Good afternoon, everyone. And it's a pleasure to be back here again among friends, homebrewers. I'm delighted to have people like Rick in the audience. It's also a problem because I was going to present a lot of his ideas as my own. But this time, I was going back and forth with Dave and said, we need to push the envelope a little and get out of our comfort zones. And one of the things that we thought that, might be of interest here is getting onto VHF and home brewing on VHF. So I thought that we'd tackle that. And in a way that we leverage our existing capabilities and techniques and see how that can be easily used to extend and get onto VHF, and why we need to get onto VHF as well. So this is going to be about that. I'm extremely sorry that the paper is not in the proceedings, because as many of you are following, there's a very tragic saga of the SBTX going on. And I was very busy with that until very late, and I could not submit the paper on time. But on VU2ESE.com, my blog site, as well as a quarterly, the QRP quarterly, you will have this access to the paper as well. So, why are we not on VHF? So I think this is the one. So I don't know if you guys have seen this before, but, Dogbert says, I've got the first video phone in the city. Then you say, okay, now we have to wait for someone else to get another one, right? And so the amazing thing is that society couldn't advance without people like you. This is precisely the challenge of VHF. Who do you talk to, right? So you've made one. And I asked this to Rick, and Rick said that I always make 2 radios. Okay. It was such brilliant stroke of genius. I said, why didn't I think of this before? So, but things aren't that bad anymore, So the first is the sun is up. So if you look at the spots of FT8, FT4, and other stuff, you'll see that there's a lot of activity going on 6 meters at least. Intercontinental QSOs are happening, and the sun is waking up and will remain up for a long time. So exactly the same thing which happens on 10 meters. You can replicate it on 6 as well, right? And you are officially on VHF when you are on 6. So that's an important one. I grabbed this just yesterday, and look at this, kilo 9. Oops, sorry, I'm sorry. Okay, oops, where did I go? Oh, here. So you can see some really, really fabulous, DX happening there. And I just picked this up from yesterday's PSK reporter. Sorry, DX Watch. But that apart, the other reason for us homebrewers and QRPers to get on to VHF is this. There are big birds flying across the sky. Okay. Now look at this, that from 1999, when the only game in town was AMSAT, you will have about 1,766 new CubeSats flying up. And all of them, unfortunately or fortunately, use ham frequencies. And many of them have transponders, have telemetry, have very interesting applications happening there that you can monitor, that you can access, etc. So there's no reason for us homebrewers, for QRPers, to not be part of this. There's always a bird above us all the time, from big ones like the International Space Station down to small CubeSats, and everybody's building them. 2 days ago, I was at the Thomas Jefferson High School in Washington, DC. They're building a CubeSat. Kids are building it. I built 2. One was a linear transponder, and the other one was an APRS stuff. So AMSAT is not the only game in town. There are a lot of other things as well. So it's important to know that there is a lot of VHF activity, even if there's no local activity going on. Then this, that antennas, as Rick showed today, can be very small, even if you are suffering from HOA and other regulations, you can still stack away small antennas. I mean, just imagine a 5-element Yagi on 40 meters or on 70 meters. It's amazing difference that you can actually try this out, and you can carry your entire stuff, go onto a field day, deploy it within minutes, have fun and come back. This particular one is the tape measure antenna. He's actually working a satellite here. The vertical ones are 70 centimeter. It's a 4-element Yagi, and the other one is a 2-meter, 3-element Yagi. All you require is a handy in this case, but we can use our own stuff. So I'm just trying to make a case that VHF is interesting for people like us. And the other reason for this is that traditionally we have shied away from VHF because we always thought that we do not have ways of measuring this. Okay, that's no longer the case, because now there are so many of these low-cost instruments, from nano VNA, which can actually go up to 1.2 gigs, I'm told now, to the tiny SA, or the Antuino, which is no longer being sold. And all this equipment is available for just a couple of dollars. For $100, you can be completely equipped to do all your VHF work without requiring anything else. Okay, so and we have had a huge legacy of these things. I hope you guys know what the one on the right is. It used to be in the 70s handbook. It was called the Connecticut Bond Box, and the one who's operating is Doug DeMoss XYL on a mountain top, and it's a 300 milliwatt AM transceiver. It was fairly common in all the 70s and 80s handbooks, until they changed the format. The Heathkit Tour, which was again an AM set. Then the IC202, which was a favorite of a lot of microwave operators because it was an SSB CW thing with a VXO, fairly low phase noise stuff. And a lot of us got the taste of our first VHF radio with a thing which was ostensibly not meant for VHF, which is Rick's 2-meter exciter. And actually, I use this for my Oscar work. Somebody had hand carried this, so these were the interesting radios which we have been building and operating. Now, how do we reboot the old BitX20? Now, by the way, the BitX is more than 20 years old as of now. Okay, it's had a good run, and it's time to up the game again. So this is the original one. And what can we do with this that can make it contemporary, and how do we get this to VHF? So that's the challenge. And I took the BitX20 because it's a well understood radio. A lot of us have built it, a lot of us have suffered it. We have modded it. We've lived with this. So now this, in the software world, there is this phrase, Jack would agree with me, called refactoring, which is you build something, you write code once and you throw it away because the first time is just to understand what you've done, and then you redo a more efficient, a more aesthetically pleasing, if I don't want to use the word beautiful, version of the same code. So how do we refactor something like this? What is wrong with this? So the way to understand a radio is, of course, not to look at the circuit diagram, but look at the block diagram itself, which is this. So this is the approximation of what you see as BitX. There's a bandpass filter, and it's bidirectional for those who don't follow the BitX groups. It's a bidirectional radio where basically on receive the signal travels from left to right and all the way right here. So it passes through the bandpass filter, RF amplifier, mixer, IF, crystal filter, second IF amplifier, detector, and BFO. Or it goes in the other direction for transmit, with the exception that there's a power amplifier before hitting the antenna. Now, this has many problems, and I'll just go back to where the problems are. So first, the bandpass filter itself has just got 2 sections in it. It's not enough. It's not enough for VHF. It wasn't enough even for HF because it allowed the images to leak through, especially on the transmit. And the image wasn't suppressed enough to meet the FCC regulations either. The other problem here, of course, was this itself. Although it has 4 diodes, it's actually singly balanced mixer. It's not doubly balanced mixer. And this is the interesting thing about singly balanced mixers, and we use them very often, that if they are not used properly, they can be extremely lossy. And that happens because of the way it works. First, in a singly balanced mixer, if you see that those 2 diodes conduct only on 1/2 of the cycle, and the other half, everything is off. So only half the time the RF energy is going through. And then to isolate the images of the 2, if you do not isolate it enough, the other image reflects back into the mixer and it causes huge problems. So that was that. And in order to figure out what was wrong here and what was wrong there, we had to add some additional gain. And this much gain was really not required here at all. Okay. And then what we also did here, and is that if you see this audio preamplifier, this is from again one of Rick's designs. It was meant to be a really minimal direct conversion receiver. You must have seen this as an example of how simple a direct conversion receiver can be in the EM RFD. But it didn't do things too well. And Rick himself documented later that, for example, this 100 PF wasn't working too well either. So, and there was all these small things. Now, if you look at this mic amplifier here, there is a collector load of 2.2K, which is feeding into a diode modulator, which actually wants a 50 ohms driving impedance for it to work well. And that's not there either. So there were all these small problems. But the bigger problem really was this. Now, I'm not sure if many of you use this tool, but it's really an excellent tool where what you do is you take all the blocks of your radio and fill up the gain, noise figure, and the distortion figures for each one of them. And you just press the evaluate button, and it gives you a fairly accurate performance figure of everything that this can do. Now, in spite of it being a fairly unthought through design, it was still giving a 2-tone dynamic range of about 88 dB. The noise figure was pretty good because there was an RF amplifier, et cetera, et cetera. So, however, I think that this can be simplified further. So just to go back here, if you look at this, and if you look at another proposed block diagram, now I have eliminated 2 amplifiers from this. There's just one RF gain stage before we actually come to the doubly balanced mixer. And somebody earlier today also commented on this, that you don't really require too much gain at all. You just require enough gain for the noise figure to be maintained. So you just keep pushing it, from one stage to another until you come here. So this is as simple as it gets with a superhet, which is you have a bandpass filter, no RF amplifier, direct double balanced mixer, diode mixer, a post-mixer IF amplifier before it hits the crystal filter, and which directly takes you to a demodulator or a modulator. So that's all we need really from a superhet. And we'll see how well this performs. So this is the one. First, we have a doubly balanced mixer on the front end as opposed to singly balanced, where the termination it's not as sensitive to termination as a singly balanced mixer would be. The only RF gain is between the front end of the mixer and the crystal filter. Then we're using an SI570 as a local oscillator. And I'm doing this for a particular reason. When you're handling something like VHF, which is completely new, you don't have to be a purist all the way through. You can afford to drop your guard. You can afford to take it easy. And SI570 is one of those chips. Now, the SI570, as opposed to the 5351, which we all love to hate, can be soldered without too much of a problem. It's got very big pads. It's got very good phase noise. The Elecraft K3S as opposed to K3, they probably charge some $200 to give you the upgrade. The upgrade is just an SI 570. There's nothing more to it. So it's got very good phase noise. And we'll use a Raspberry Pico as a radio controller. I'll also come to why we need to do that. But essentially, I think the audio is going up. Okay. The Raspberry Pico, as opposed to an Arduino, is miles ahead. It's the difference between a toy radio control car and an actual Hummer. And I mean it really. You know, if you look at the size of the memory, the size of the CPU, the speed at which the Pico can go with 2 processors as opposed to the Arduino, which is as old as the BitX, it's about 20 years old. So there is no reason to anymore depend on an 8-bit 2 kilobyte RAM, you know, microcontroller, when for actually lesser price, the Pico CPU is only 60 cents. So now in this here, if you see, there's very little gain happening here. Bandpass filter is -5, mixer is -6. The amp here is about 15, including the attenuation pad. The crystal filter is -10, and I'll tell you why it's so high. It's very interesting reason. Then the detector and that audio amplifier. So if you look at this, the signal, you know, coming from here to the audio amplifier, it's almost the same as what came into the antenna. So it's one of the few places where for a superhead, the audio preamplifier is very critical to how well it works, because all the gain is starting from here on. So usually you don't bother about it. You drop in a 2N3904 or something like that. But here you require a low noise transistor like a BC547 or something like that. By the way, I also figured that a lot of RF low noise transistors do not necessarily have low noise in the audio range. So we tend to use those, but they don't really work that way. Okay, so this is the circuit diagram in all its glory. It's very simple, as you can see, far simpler than anything else. You have an AD1 mixer here, right up in the front, being driven by an SI 570. And this actually is a very interesting thing here. You know, I'll just take a slight detour. We were told that you need to put a low pass filter between the SI 570 when it's driving, any square wave when it's driving an AD1 mixer. But I don't know why. I have a theory about it. A square wave gives far better dynamic range. And I think that happens because it very quickly transits from being, you know, totally off to totally on with the diodes. So if you're driving it hard and you have enough drive, a square wave feeding the diode mixer is doing pretty good job. So that's what's happening here. And we have a duplexer here before it hits the IF amplifier. Now, if you consider this working at VHF, there are products coming out of this mixer which are at VHF and probably UHF as well. For example, if something is coming at 145 megahertz in here and you have something at 130 megahertz, the output mixer will also be at 130 plus 145, right? And when it hits the IF amplifier, these are 2N2222s. They do not hold the 50 ohms termination properly. So you do not allow the UHF energy to pass through to the IF amplifier. You want it to ground off through this resistor with a very low coupling capacitor so that only the UHF goes in here. This is actually, this needs to be designed. You cannot put an arbitrary value here. It's a duplexer. So we put this through this IF amplifier, and then we have a crystal filter here at 27 megahertz. You require 27 megahertz because the images should not be very close by when you're going to VHF. So you need to take as high a frequency as you can. But the problem with the high frequencies is that you cannot design very narrow filters. And the trade-off is usually loss versus bandwidth with low Q crystals. So which is why you are having a fair amount of, you have to, you know, take in almost about 10 dB of loss here. But that's fine because you already have about 16 dB of gain here between this IF amplifier and the attenuator put together. And then it's a little unusual, but you take the output of the crystal filter and directly go to a doubly balanced diode detector. This here is again Rick's design. This is Rick's design. I have to disclaim here. So it's a fairly simple crystal oscillator, but it was there in the micro R1, so we still have it. We put up an inductor here to pull this. Now, this is the interesting thing. If you look at a crystal filter here, and imagine that instead of these crystals, you're looking at inductors, it's actually a low-pass filter, right? It's a low-pass filter. But if you then think of the crystal as an inductor with a capacitor in series with it, then it starts becoming a bandpass filter. However, the characteristics of a crystal filter or ladder filter is actually low pass, which essentially means that it has a very sharp cutoff on the higher side and a sort of a gentler slope towards the lower side band. So which is why you have to pull this crystal up and keep it on the higher side of the crystal filter, right? So it becomes an LSB radio. But on VHF, we mostly work with USB. So the sideband inversion is actually done by flipping the frequency of the SI570. If this goes onto the higher side of the RF, the sidebands are automatically flipped around. So that's actually the trick that we use here to go between the sidebands. We do not change the BFO's frequency, but we flip which side of the RF the local oscillator is operating. Okay. Then this particular audio preamplifier was recently published by VU2ESE about 1.5 or 2 years ago. Actually, if you look at this and you look at this guy, they're almost the same because they are feedback amplifiers. The usual stuff that we've been using all the time with superheads or with direct conversion receivers is a common emitter amplifier that we first saw with W7EL's, that small wonder, the optimized 7 megahertz QRP transceiver. The problem with that one was that it was biased for only 0.5 milliamperes of current. Now, how does it matter on VHF? Well, it matters with the new modes which are coming in. The FT8 has all the activity of the band within 3 kilohertz, which will actually pass right through this and hit the audio preamplifier. So the audio preamplifier cannot afford to overload on a couple of signals when you're actually interested in the weaker signals there, which is why this is biased for fairly high current. It's a feedback amplifier with a common emitter, and it's feeding an LM386 right now. But it's best that we actually use a couple of bandpass filters actually here, active bandpass filters, followed by an audio amplifier. And the reason for that is this is actually pretty broad. This is about 3 kilohertz. And all the time you don't require that, especially on VHF when you're trying to listen to really weak signals. And you'll see this problem there when I play an audio which I recorded from this or this. And here is the modulator where you have an emitter follower following the mic amplifier, so that you have a 47 ohms robust impedance driving the modulator. So actually, if you see this, it's pretty simple. It's as simple as it gets, right? And because we are using an SI570, you can expect that on this end, you have the VHF signal coming in and out of it. So this is what it looks like. It's pretty small. And the way we built it is, so actually, it can all be built into just one small PCB, because there isn't much here at all. Usually, I start building it from here, and by the time I'm here, I run out of space. So you can see that there's a lot of, it's completely jammed up here. Now, there are a couple of other tricks here, because you're using a Raspberry Pi, which has got digital noise coming out of it. I actually built the Raspberry Pi on the other side. And if you can see that there is just one wire which shorts this ground to the other side. Oops, sorry. It's about here. So the reason why we do this is to actually avoid the digital hash. The digital ground and the analog ground ought to be separated. That's actually very important. So let me just go back to this. And here you will see that I have used a different symbol for the analog ground and a different one for the digital ground, and there's just one connection between the two. So this is actually a tricky thing which you always need to take care of when you're putting digital electronics along with analog electronics. So it's small, as I showed you. I'm using an OLED display here. And this is the VHF, this is the development of the VHF bandpass filter. So you know this, that you have an LC combination, let's say 3 resonators you're using, where the energy is being coupled from one to another. And to couple it, we use capacitive coupling. That's one way of doing it. There's actually another very interesting way of doing it on VHF, which is not controllable really, which is just to keep these LCs near each other and allow mutual coupling, which you will otherwise fight in other designs. So you can actually use it, but it's never under your control. So it's not recommended. So now the kind of shape that the filter takes depends on these two value of these two capacitors and the characteristic impedance that you're looking at both ends. And there are various ways of doing it. There is Chebyshev way of doing it, the Butterworth, etc. I'm not getting into that, but you need to couple them. And these values have to be very small. Now, if you recollect, for example, if you take Hans's bandpass filter for 14 megahertz, I think the coupling is about 2.2 pf. So if you scale it up to 2 meters, it's going to be 0.22 pf. Now, where do you get a 0.22 pf from? So instead of that, what you do is you tap down here like this. Okay, and then couple this tap down values. And for the end terminations also, you can just tap it down. So this is actually how it finally looks. And you can actually simulate this. Let me just see where that is. Yeah, that's a simulation on EMRFD's LAD build. So you put this in together, and then you can see how good it looks here. It's about 0.4 or 5 dB is the loss here. And the way you make it is like this. You take a double side PCB and you drill as many holes as you can. Okay. And then these are the pads. These are 7 pads. Now, if you look at here, 1, 2, 3, 4, 5, 6, and this is 7, right? So you require 7 pads here. So these are 7 pads, and it's important to also have ground quite close to them. And this is a little bit of an artisanal thing, that you have to put all these capacitors only on one side. Okay, don't put it on both sides. Otherwise, it will act like a sort of an inductor from one side to the other. So you short the 2 sides of the PCB and you put this in. Now, it's very important to have good quality capacitors here. And this is one of the times when you have to just shut up and use SMD. There is no way out. There are big SMDs available, 1206. They are the size of a quarter watt resistor if it stands up like that. Pretty easy to solder. So there is no reason to shy away. It's about time you order about a strip of 100 of 2.2 pfs, 10 pfs, 22 pfs, 100 pfs, and just put them in the junk box. And you can always do that. Okay, this is the power chain. So we have already seen the VHF bandpass filter. And this I've sort of standardized on just one way to build all these coils, which is you take a quarter 20 bolt and basically wind a number of turns on those. And there are utilities online which will tell you the inductance, and the inductance is actually very exact on air inductors as opposed to toroids, because the material mix at times varies, etc. But this, you will get it pat on. The only problem might be that the exact value that you want will not be in those integral number of turns. So tuning it is simple. What you have to do is grab the ground end of the coil, okay, with a long nose plier, and heat the soldering point and just pull it until it resonates. So you put your VNA on and do that, or you can use toothpicks to basically pull and push the things together. And VU2ESE actually wrote a very good article on how to tune a triple tuned circuit. but I'm too lazy to do that. So I just keep pushing and pulling it until I get a peak, and that's it. Now, the other thing is this, that you have these 4-legged critters. Let me show you this, right? This costs less than $1. Okay. What I've done is I've pulled these 2 legs up, which is 1 and 3. And one is input, the other is output. It gives you 20 dB gain, and you just need to put an inductor and a resistor bias. I'm sorry, this circuit is wrong because it's coming from the data sheet. There ought to be no capacitor here. The capacitors have to move in there. So it's fairly simple to use. And this is what we have done here, that each one of them is giving 20 dB gain. But if you put both of them together, there is no robust impedance between the two. So you actually put a 6 dB pad, which is good enough, followed by either a 2N3866 or a 5904. This gives about 300 milliwatts. Now, if you realize what we've done until now, there is another very interesting thing. This will actually work on 5 volts, 5 to 9 volts. We've been living in this 12-volt era for too long. There is no reason to stick to that. 5 volts, 9 volts are good enough. And especially with the LiPo batteries coming in, you get a 7.2-volt LiPo battery, which is really good for this kind of a thing. So, and on the receive side, to take the FM broadcast out, you need a single resonator at least. Pre-selector, it gives about half a dB loss here, followed by 20 dB gain on the AG303. So this actually has a noise figure of 5 dB. And all this is actually pretty easy to do even with the ugly build. Now, if you look at this is pretty simple, right? That's your triple tuned circuit. As you can see, this is where I've been tuning it with. There are these very thin copper sheets. I think they're used in transformers. I'm not sure where they're used. So that's the thing. And you'll see this entire series of solders all around here. And this is one mimic. There's another mimic here. And this feeds to the transistor. There's a low-pass filter. For a long time, I agonized over how to do the TR for the transmit receive, but I figured that a regular relay is good enough, but you have to make it very close. For example, if you look at this SMA, it's directly soldered onto the pin of the diode itself. And where there's a longer path, you just use a coax here. It's an RG174 coax. And this end goes and it basically attaches itself to the core that you saw. So it's not too difficult at all. In fact, you have to wind lesser coils than you would do for an HF, which for me is a great deal. So now, having said that it's for VHF, there are a lot of interesting things that you can do with this. Okay, first is you can go analog. Okay, so let me just show you what to do there. This is all you need to do. You need to just take out the Pico and put in a VFO directly. And being an AD1, it can actually work with even 0 dBm input. So this will form a regular HF superhead if you choose to. Fairly simple to do. Then there would be no digital electronics involved at all. Find some way of tuning this and you're done. The other is this, where I'm not sure whether you can see, but this is an SDR now. It's an SDR because what you do is you take this. First, you open this bandwidth up to, let's say, 20 kilohertz. Then you tap off the audio preamplifier and feed it here to the ADC of the Pico, where you can do all your processing, your DSP processing, then take the output and then feed it back to the audio amplifier. This is an option that you can do. So it can be an analog transceiver as it works, but you can keep adding AGC, CW filtering and all that to the same design if you want to. The third is, yes, this is the one. So here it's UHF. Now the same thing is working on 70 centimeters. And the way it works is like this. The ADE1 can also become a harmonic mixer, fairly simple, right? So it will also, all you need to do is, instead of, for example, 435, right? At 435, the IF is 27 megahertz. So 435 minus 27, what's it, 403, I don't know, yeah, 405. No, 405 would be 30, 408, right? 408. So 408 megahertz is the local oscillator you need. You actually drive it at 1/3 of that frequency, 408 divided by 3. That's all you need to do, okay? What happens there is that the ADE1 has a loss of not -5 or -6, but -15 dB. Okay. All you need to do is just add one more layer of amplification. That's all, both ways. So this provides 20 plus 20 dB. The good thing about UHF is you don't have to fiddle with any coils. For about 50 cents each, you get these SAW filters for 433 megahertz, which work perfectly well at 435 as well. So they're like a crystal filter, which is what I've done here. So if you look at the receiver, there is a SAW filter up front, about 40 dB gain, and another SAW filter, and you're done. On the transmit side also, there is one SAW filter which is common to transmit and receive. Then it goes to the second SAW filter after the drivers. And you can use an MAV11, which will give you about 100 milliwatts of output. And 100 milliwatts of output is plenty. And I'm telling you it's plenty because your AO91 and 92 were giving out about 100 milliwatts. That's all they were giving out. So there is no reason for you to think that, you're really QRPP or whatever the new acronym for that is. So it can go in various ways, provided you're starting with a fairly simple superhead, and it works pretty well. So Andy, could you just play the audio? Yeah. So this was the first QSO actually I had with this in my car, and I'm about 7 kilometers from my friend who's running a slim gym from a fairly high building, and I'm on a quarter wave whip inside a car. I think that MP3 is the one, I think. The one on the left, yeah, top. Yeah, yeah. Yeah, that's a big.
To Bravo Victor Bravo, this is VU2 Echo Sugar Echo. Thank you, Enu, for the first call on this radio. I'm calling this the Dayton radio because we've built this for Dayton. So give me another call to see how your audio sounds. VU2 Bravo Victor Bravo, this is VU2 Echo Sugar Echo.
Yeah, VU2 Echo Sugar Echo, VU2 Bravo Victor Bravo. Yeah, nice campaign. And coming fine and beautiful signals. Audio quality also very good. VU2 Echo Sugar Echo, VU2 Echo Sugar Echo, VU2 Bravo Victor Bravo.
Roger, Venu. So this is actually a modern version of Vitex radio. And what we have done here is that I've simplified the design and also made it such that it can work from 70 centimeters down to LF frequencies. So I will now drive around and let's see how the range is of this set. VU2 Bravo Victor Bravo, please QRX. This is VU2 Echo Sugar Echo.
So anyhow, so that's the one. You saw that the filter was a little too wide and it requires trimming, but I think the trimming is best done at an audio frequency. So if it's just an audio low pass filter with a cutoff at about 2.2 kilohertz or so, that this would be done. So that's it. Thank you very much. I'll take some questions. Thank you. Sure. Yes. Okay. Yes. AG303. Yeah. So the MAR have lower gain per device, and this one was very cheap. That was the only reason I got 100 of them for about $40 on Mouser. So I have another 90 to go. I did, which is why you saw that there was a pad between two of them when I was cascading them. But the good thing about Mimics is because the input and output impedances are very low. Okay, as long as you're terminating it properly, you will not have any problem with oscillations. Yes, of course. Yeah, yeah. Absolutely, absolutely. Yeah. Anybody else? Sure. Right. Well, I've used the CMOS versions. Yeah. I think it's BBC is the suffix for that. Yeah. Oh, CAC, I'm not sure. I mean, it's one of those two. Okay. Any more? Okay, thank you so much. I have the radio here if someone would like to see this.